All right, team, this is part 2 of that 2-part video about electrons and orbitals and electron configuration. So this is where we left off in the last video. We were talking about orbital filling diagrams and how the periodic table is structured to help us figure out, how many electrons go where and where all the sublevels are. So we're going to go from this orbital filling diagram into something called electron configuration. Now, electron configuration is basically just a condensed version of the orbital diagrams. So we're going to take everything from the orbital diagrams and condense it into a shorter version because chemists are lazy. So essentially, after listing the energy level and the sublevel, so like we did 1s, but we drew a box for that, instead we're just going to write 1s, and then we're going to list the number of electrons that were in that orbital as an exponent. So for example, 1s can hold 2 electrons, so if it's full, we would just put a 2 there as the exponent. So if we go back to the examples we already worked out for the orbital filling diagrams, I'm going to write the electron configurations in a different color here. For hydrogen, it's super easy. You just take that 1s, and there's only 1 electron in that orbital, so we write 1. So it's 1s1, that's the electron configuration, and you're done. For helium, it's 1s2. Because now we have 2 electrons in that orbital. Moving down to carbon, okay, we're literally just condensing everything that we see here in the orbital filling diagram. So 1s, and it's full, there's 2 electrons there, so we write 2. Then we're done with that, so now we're on to the second, we're on 2s, and it's full. We have 2 electrons, sort of, got kind of messed up there. Then we're moving on to the 2p. The 2p is not full. It has 2 electrons, so we write 2p2. And if you look at this, it should match exactly with what's happening in your periodic table, which mine is a bit of a mess up here, but carbon is right here. It's the second element in the 2p sublevel. So it makes sense that we would end with 2p2. Oxygen is very similar to carbon, 1s2, 2s2, but it's 2p4 because it's the 4th element in the second p sublevel. Copper, again, I'm condensing everything. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then over here in the 3d, remember we only have 9 electrons there, so it's 3d9. So if you have the orbital filling diagram, it's really easy to write the electron configuration because you're just condensing it. But you don't have to have the orbital filling diagram in order to write the electron configuration. All you need is your periodic table. For example, over here, I have niobium. So niobium is Nb. So on the top right here, it's this element here. If we label this all out, this is in the 5th energy level, but it's in the D sublevel, and we know that in the D sublevel, this is actually 3D, and this is 4D. So we know that we should end up with 4D something. But then we're just like reading the periodic table, left to right, top to bottom. So we start with the 1s, and we're going to fill it up. So 1s2. Then 2s2. What comes after 2s2? 2p6. And then 3s2. Remember, after 3s2, we don't go to 3d10. We go all the way across to 3p, and we're filling it up, 6. Then we're at 4s2. This is where we switch, right? After the 4s2, we go to 3d10. After 3d10, we're back in the 4th energy level, the p sublevel, and we're filling it up, 4p6. Now we're in the 5s2, we're filling up that 5th energy level, and then niobium is the 1, 2, 3rd element in the 4d sublevel. So we write 4d3. And that's how you write the electron configuration. I'm going to do it again for bismuth. I am not going to talk all the way through it because it's very long and I will get tired. I'm just going to write the whole thing, and then you can hopefully see how it follows along on the periodic table. All right, I jumped back in here because once we hit the 6th energy level, things get a little bit weird. So I just finished writing 5p6, which ended me at xenon. So now I'm in the 6th energy level, and I'm actually running out of room, so I'm going to go just below this. We start with 6s2. But then we start the lanthanide series. So 6s2 goes here, but then we jump down to the 4f sublevel. And we fill that whole puppy up. So 4f14, the whole thing gets filled up. And then we're back up here in the D sublevel, and it's the 5D. That whole 5D sublevel gets filled up. So I go all the way across. And then bismuth is in the 6th energy level, P sublevel, and it's the 3rd element. So that's how you finish that whole thing up. Now, you might have realized that this is a whole thing, right? This is very long. But of course, your chemists are lazy, so we came up with an abbreviated way to write the electron configurations. To abbreviate, you're going to find the previous noble gas. So the noble gases are your column 18. So that's the very last column on your periodic table, starting with helium and going all the way down. Those are your noble gases. So you're going to start there. You're going to write that number or that element in brackets, and then continue your electron configuration from there. So it's sort of like a short stop. So for potassium, potassium's right here, the previous noble gas, we would have to go back to the 3rd energy level, and all the way at the end would be argon. So we will write Ar in brackets, and then continue our electron configuration from that point. By writing argon in brackets, we're saying like, hey, this is the electron configuration for argon plus whatever comes next. Luckily, it's very short. Potassium is just 4s, and it's the first one, so that's 4s1. Now, to do antimony, antimony is over here, so it's in the 5th energy level, so we're going to go back to the noble gas from the previous energy level, so that's krypton, and we write Kr in brackets, and then we continue the electron configuration from that point. So starting here in that 5th energy level would be 5s2, okay, then we go to 4d10, because we're traveling across the periodic table here, so 4d10, then we're back in 5p3, because antimony is the 3rd one. To do roentgenium, that is all the way here at the very bottom of your periodic table. So the previous noble gas is radon. So we write Rn and then continue the electron configuration from there. So it'll be 7s2. Okay, then we have to jump down to that F sublevel, 5f14. And now we're back up here, going to go through the D sublevel. So it'll be 6d. And then roentgenium is the 9th element in that 6d sublevel, so we write 6d9. And that has saved you so much time and energy, so that's why we write the abbreviated. Unless I tell you to write the abbreviated electron configuration, you should always write the full electron configuration. So make sure that you're paying attention to instructions to see if I'm asking for the full or for the abbreviated. Now, moving on, we need to talk just a little bit about our valence electrons. So the valence electrons are the electrons that are in the outermost energy level of an atom. So that would be the S or the P sublevels. Okay, because if we look at any of these electron configurations, so for example, the electron configuration for bismuth here, the outermost energy level would be the 6th energy level, and you'll notice that it's only got this S and the P orbitals there, because the F and the D are lower energy levels, the 4th and the 5th respectively. So that outermost energy level will only ever include the S and the P sublevels. And those are the electrons that determine the chemical properties of an element, because those are the valence electrons that actually participate in chemical reactions. And we can determine that number of valence electrons simply by looking at the column that it's in on the periodic table. I've got a periodic table for you here. If I was to really quickly sort of jump through the electron configuration of, say, the 2nd energy level here, it would be 2s1. This would be 2s2. Over here I've got 2p1, 2p2, 2p3, etc. So if I add this up, the most number of valence electrons I can ever have is however many can fit in an s plus however many can fit in a p. So total, you can only have 8 valence electrons max. And this is very important. You can only have a max of 8 valence electrons. And if we add that up, you'll actually see on your periodic table, there's a bit of a shortcut. Group 1, so a group is a fancy name for column. So it says group 1 on your periodic table. Everything that's in group 1, every single element will end with an S1 electron configuration. So they will all have 1 valence electron. Everything in group 1 will have 1 valence electron. Similarly, everything in group 2 will have 2 valence electrons because they'll all end in S2. So these will all have 2 valence electrons. I highly recommend writing this onto your periodic table. So group 1 is all 1 valence electrons. Group 2 is all 2 valence electrons. Then if we jump over here, we're going to skip over the transition elements right now, this group in the middle of the D sublevel. We're going to go over to the third energy level, so the third column. Your periodic table probably says group 13. I don't have it in front of me at the moment, unfortunately. It probably says 13. So if we look at that, we can just look at the 3. So in this third column, we'll have 2 electrons from the S sublevel plus the 1 electron from the P sublevel. So total, we will have 3 valence electrons. When it says P2, remember we've got the 2 from the S, the 2 from the P, so this column will have 4 valence electrons, and so on and so forth. The very last column, I called them the noble gases. We call them the noble gases because they're sort of better than the rest of the elements because they have the maximum number of valence electrons, which means they're very stable. That 8 valence electrons is very stable because it's a full sublevel. We filled up the S, we filled up the P completely, and that will always be more stable than having a half full or a partially full sublevel. We can abbreviate those valence electrons around an element as another way of notating where the electrons are in an atom, and that's called the electron dot diagram. These are also known as Lewis dot diagrams, and they show the atomic symbol of the element with dots around it to symbolize those valence electrons. Now, like I just said, there can never be more than 8 valence electrons in a neutral atom, or in an ion, to be honest with you. There can never be more than 8 valence electrons in an atom or an ion. So we'll just cross that out. Okay, never more than 8 valence electrons. Let's look at some examples here. So nitrogen, if you look at your periodic table and you find nitrogen, you'll see that nitrogen, if we were to write the electron configuration, it would be, let's say start with helium, the previous noble gas, and then it would be 2s2, 2p3. So total, we have 5 valence electrons. So when we write the electron dot diagram, we're going to start with the symbol, which is N, and then we're going to add 1 electron to each side, if you will. So 1, 2, 3, 4. Remember that we don't want to double up until every orbital is full. So this is our 1s orbital and then our 3p orbitals. So we've just applied Hund's rule here. Each orbital is singly occupied before one is doubly occupied. But now I'm out of room, right? I've added 1 to each side. So now I'm going to add my 5th electron to the left over here. And now I've got my 5 valence electrons. And this is my finished dot diagram for nitrogen. Now neon is a noble gas. Neon has 8 valence electrons, judging by the column that it's in, and because its electron configuration would end in 2s2, 2p6. So it's got 8 valence electrons. So when I write the dot diagram, I write the symbol Ne, and I add 1 electron to each side. 1, 2, 3, 4. Then I double up. 5, 6, 7, 8. And now it's full. I cannot add any more electrons to this atom. Copper. Now copper It's in that transition metal area, that D sublevel. Now, if I go back to this periodic table here, you notice that I skipped over this section. Let's come back to it very briefly. So this section, let's see, if I wanted to write the electron configuration, like for example, this would be 4s1, 4s2, and then I would go to 3d. So I don't have anything in the 4p. I just have the fourth energy level, which is the outermost, and it always will have 2. So any element that's in the middle here will always have an electron configuration with the outermost energy level being filled, an S2, a full S sublevel. Everything in the middle here, including down here in the F sublevel, will always have 2 valence electrons from that. So for copper has, we assume, 2 valence electrons, so we write 1, 2. And that's the dot diagram for copper. Moving on from that dot diagram, we have something called the octet rule. Now, the octet rule states that atoms prefer to have 8 valence electrons. And as I talked about before, that's because that full sublevel is very stable. So when we have that full electron configuration, that full orbital filling diagram, it's just more stable. So chemical reactions actually occur because atoms are trying to lose or gain electrons to become stable. They want to get to that magical 8 valence electrons. Ions are actually more stable than their atom counterparts because ions will always have 8 valence electrons. Any atom will always lose or gain just enough electrons to get to 8. So let's start with the electron configuration for sodium here. So if I write the electron configuration for sodium, so you'll notice that it has this partially full sublevel here. And if we draw the dot diagram for it, this is our outermost energy level. It just has 1 electron. So the dot diagram for sodium just looks like this. Now, if I were to make sodium 1 plus, remember, to get a positive charge, we take away an electron. So I would have a very similar electron configuration, but now I essentially took away that 3s1 electron. So now I have a full second energy level, which is very stable. This goes by the octet rule. So I took away that electron from the dot diagram, and I'm left with just a positive ion here. Essentially, I have sodium that's short 1 electron, and that is more stable. Another example, this time we've got a negative 1. So if I have fluorine, the electron configuration for just regular fluorine that's neutral is 1s2, 2s2, 2p5. And if I wanted to write the dot diagram, I would see, okay, I have 7 valence electrons in that outermost energy level. So 1, 2, 3, 4, 5, 6, 7. So it's like I have an empty hole right here for fluorine. So if fluorine gains 1 electron, it'll form that 1 negative charge, and its new electron configuration would be 2p6. So we'd have that full second energy level, which is ideal. Then we could have 8 valence electrons, and it would have a 1 minus charge. And that's all I have for you in this part 2 video. So please email me if you have questions. Please don't forget that you can rewatch the video at any time. And I hope to be hearing from you, and look for practice with this material and the orbital diagrams in the coming days.